how to measure voltage, the difference between direct and alternating voltage as well as current, and finally we'll briefly look at why and how voltages vary around the world. We learned that electricity is the flow of free electrons between atoms. Voltage is what pushes the free electrons around a circuit. Without voltage, the free electrons will move around between atoms, but they move around randomly, so they aren't much use to us. It's only when we apply a voltage to a circuit that the free electrons will all move in the same direction, causing current. It's easy to imagine voltage like pressure in a water pipe. If we have a water tank completely filled with water, then the mass of all that water is going to cause a huge amount of pressure at the end of the pipe. If we have a water tank that's only partly filled, then there will be much less pressure in the pipe. If we open the valve to let the water flow, then more water will flow at a faster rate from the high pressure tank compared to the low pressure tank. The same with electricity. The more voltage we have, then the more current can flow. Voltage can exist without current. For example, we can measure the pressure in the pipe with the valve shut with no water flowing, and from this we can tell that the pipe is pressurized. What we're really measuring is the pressure difference between what's inside the pipe compared to the pressure outside. The same thing if we have a battery connected to a circuit with an open switch. The voltage is still present, we can measure that, and as soon as the switch closes, it's going to push the free electrons around the circuit. We sometimes hear voltage referred to as potential difference. This really means how much work can potentially be done by a circuit. Coming back to our water analogy, if we have two lakes at the same level, then there is no potential to do work because the water isn't flowing. But if we raise one lake higher than the other, then this higher lake now has the potential to flow down to the second one. And if we give it a path, then it will flow. If we place a turbine in its path, then we can use its energy to power a light or even an entire town. Back to the electrical circuit, this battery has a potential difference of 1.5 volts between its negative and positive terminal. If we connect a piece of wire to both terminals of a battery, then the pressure of the battery will force the electrons to flow all in the same direction along the same path. We can then place electrical components in the path of these electrons to do work for us. For example, if we place a lamp into the circuit, then this will light up as the electrons flow through it. If we then added another battery to the circuit in series, then the electrons will effectively be boosted by the second battery because they can only flow along this path and there is more energy being added. This will combine the voltages so we get 3 volts. More volts equals more pressure, which means more pushing force. That will mean more electrons will flow and the lamp will glow brighter. However, if we were to move the battery and connect it in parallel, then the path of the electrons splits. Some will flow to the first battery and some will flow to the second battery. Therefore, the batteries will both provide the same amount of energy, so the voltage isn't combined. The voltage isn't boosted and we only get 1.5 volts. So the workload is split by the batteries and the lamp will be powered for longer, but it will be dimmer. We've covered this in much more detail within our electrical circuit series. Do check that out, links are in the video description below. We measure the potential difference of voltage with the units of volts, and we use the symbol of a capital V to show this. If you look on your electrical appliances, you will see a number next to a capital V indicating how many volts the product is designed for. In this example, the manufacturers of this USB hard drive are telling us that the device needs to be connected to a 5 volt DC or direct current supply and it needs 1 amp of current for the device to work. The term volt comes from an Italian physicist named Alessandro Volta, who invented the voltaic pile, which was the first electrical battery that could provide an electrical current in a steady rate in a circuit. Voltage and volts are different. Remember, voltage is the pressure and volts is just the units we use to measure it in. The same as we know the pipe has pressure, but we use units to measure this pressure such as bar, PSI, kPa, etc. As we saw earlier, we can measure volts with a voltmeter. This can be separate or part of a multimeter. If you don't have a multimeter yet, you can pick one of these up really cheaply. I highly encourage you to have one in your toolkit. I'll leave a link in the video description down below for where to get one for a good price. To measure voltage, we have to connect to the circuit in parallel across the 2 points we would like to know the voltage or potential difference for. So for a single battery in a circuit, then we measure 1.5 volts across the battery, and we also measure 1.5 volts across the lamp. The battery is providing 1.5 volts to the lamp, and the lamp uses 1.5 volts to produce light and heat. In a 2-lamp series circuit, we measure 1.5 volts across the battery, 1.5 volts across the 2 lamps combined, but 0.75 volts across the lamps individually. The voltage or potential has been shared between the lamps to both provide light and heat. The lamps are dimmer because the voltage has been shared or divided. Again, we'll cover this in more detail in our electrical circuits tutorials. So we saw earlier that voltage and volts are different. Voltage is pressure and volts is the unit of measurement. So what does 1 volt mean? 1 volt is required to drive 1 coulomb, or approximately 6,242 quadrillion electrons, through a resistance of 1 ohm in 1 second. That's still a little confusing, so another way to explain this is that to power this 1.5 watt lamp with a 1.5 volt battery would require 1 coulomb, or 6,242 quadrillion electrons, to flow from the battery and through the lamp every second for it to stay on. To power this 0.3 watt lamp with a 1.5 volt battery would require 0.2 coulombs, or approximately 1,872 quadrillion 600 trillion electrons, to flow from the battery and through the lamp every second for it to stay on. If we try to use a lower voltage, the lamp would turn on, but it decreases in brightness as the voltage decreases. That's because there is less pressure to force electrons through it. Less electrons flowing, less light that can be produced. The lamps are only rated for a certain voltage and current. If we use a higher voltage, then the lamp will become brighter because more electrons are flowing through it. But if we add too much voltage and current, then the lamp will blow because too many electrons try to pass through at once. If we look at some typical batteries, we can see that this AA battery has a voltage of 1.5 volts, and this one has a voltage of 9 volts. These are sources of direct voltage, meaning the pressure it provides moves the electrons in a constant current in one direction, much like the flow of water down a river. We covered this in our last video on electricity basics, so do check that out if you haven't already. Links are in the video description below. Direct voltage is usually represented with a capital V with some dots above this and a small horizontal line. You can see an example of this on the multimeter for the setting we would need in order to measure the voltage in a DC supply. If we plotted this voltage against time, it would produce a straight line because it is constant, it is direct in one direction. The voltage in our wall sockets is alternating voltage. This is a different type of electricity. In this type, the electrons alternate between flowing forwards and backwards because the polarity of the circuit is changing, much like the tide of the sea. If we plotted this voltage against time, we would get a sine wave as it moves forwards and rises to its maximum and then starts to decline. It passes through 0 and now the current is flowing backwards, but it then hits its minimum and reverses direction again. This is usually represented with a capital V with a wave line above it. You can see that on the multimeter here also for measuring AC voltage. The voltage at these sockets varies depending on where in the world we are. The majority of the world uses 220 to 240 volts, but North, Central and some of South America, as well as a few countries scattered across the planet, will use 110 to 127 volts. We can measure the voltage at our sockets and see that it actually changes slightly throughout the day as the demand on the electricity network varies. And we can do that using one of these cheap energy meters. Again, links in the video description down below. If you want one of these, you can pick them up fairly cheaply and they're a great device for your toolbox. The reason for different voltages around the world goes all the way back to the beginning when electricity first started being distributed. At first, there was no standardization, so each distribution network had its own voltage and frequency for whatever their engineers felt was best. Eventually, over time, some companies grew and dominated the market, and so voltage and frequency standardized as their products and services expanded. Governments also had to step in and pass laws and regulations to help standardize their countries so that people could buy products easily, but also trade products with other countries. This is still a problem to this day, but it's pretty much too late to fix as everyone is now so reliant on their electrical devices, and we would need to replace or modify them all to solve the problem. For example, if we take a hairdryer from the US, which is rated at 110 volts, and we plug it into a wall socket in Europe which has 220 volts, the hairdryer will burn out at full power because there is just simply too much voltage or too much pressure and the device just can't cope. If we took a hairdryer from Europe and plugged it into a US socket, it probably won't turn on, but if it does, it's not going to be very strong. It's going to be pretty weak because there just isn't enough pressure for it to function. Some products can be used in different voltages though. You need to check the manufacturer's labels on the product to first see if the product has been designed to cope with different voltages. For example, this laptop charger shows that it can be used on voltages between 100 and 240 volts, whereas this charger is only rated for 220 volts or 240